Stand on the surface of Mars for just one moment and you will feel something utterly unexpected. Not terror, not alienation, but recognition. The sun rises, the sun sets, day turns to night. The rhythm feels oddly familiar. Because a Martian day, what scientists call a soul, lasts 24 hours, 39 minutes, and 35 seconds, nearly identical to our own terrestrial clock. Close enough that your body would barely notice the difference. Close enough that when humanity finally sets foot on that rust-colored surface, our circadian rhythms will not betray us. This is no accident. This is Mars offering us a gift, a psychological anchor in an otherwise hostile universe. But the familiarity does not end with time. Mars tilts on its axis at 25 degrees, almost perfectly matching Earth's 23.5 degrees. This celestial alignment guarantees something remarkable: seasons. Real, distinct seasons, just like home. The polar ice caps expand and contract. Temperatures shift with the passing months. Dust storms brew and dissipate with seasonal regularity. The Martian year stretches across 1.88 Earth years, making each season impossibly long. The pattern remains recognizable: winter, spring, summer, autumn. Mars breathes with a rhythm we understand, yet beneath this comforting resemblance lies a world fundamentally alien in scale and physics. Mars is small, diminutive. Its diameter measures only 6,779 kilometers, roughly half that of Earth. This difference is not merely cosmetic. It translates directly into a gravitational field 62% weaker than what we experience at home, comparable to the gravity of Mercury. Imagine stepping onto the Martian surface weighing 100 kilograms on Earth. The scale beneath your feet would register only 38 kilograms. This profound reduction in gravity dictates everything. The way buildings must be constructed, the way bones will weaken over time, the way humans will walk, run, and eventually leap across the landscape in ways impossible back home. The planet's signature color, that iconic reddish-brown hue, visible even from Earth with the naked eye, tells a story of planetary aging written in chemistry iron oxide. Rust. The surface of Mars is drenched in iron minerals that have spent eons reacting with oxygen, creating a fine, pervasive dust that blankets the entire globe. This deep oxidation is not just aesthetic, it is a chemical signature of immense geological interaction, a history etched into the very soil. Walk across Mars, and you walk across billions of years of planetary memory. The temperature extremes are equally punishing. Near the equator during summer, the thermometer can briefly touch 35 degrees Celsius, almost pleasant, almost survivable. But at the winter poles, temperatures plummet to a bone-chilling negative 143 degrees Celsius, cold enough to freeze carbon dioxide solid, cold enough to kill any unprotected human in minutes. Mars is a world of contradictions, familiar yet alien, welcoming yet deadly. And nowhere is this duality more apparent than in its geology. Because Mars does not merely host mountains and canyons, it hosts monuments, impossibilities, structures so vast they dwarf anything Earth has ever produced. Consider Olympus Mons, the largest volcano in the entire solar system. It towers 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. But its height is only part of the story. The volcano stretches 600 kilometers across, so wide that if you stood at its summit, you could not see its base. The curvature of Mars itself would hide the volcano's true shape from your eyes. The flanks slope gently at only 5 degrees, creating an illusion of flatness until you reach the edge. And there, the ground simply drops away, a sheer cliff plunging 8 kilometers straight down. Why does Olympus Mons exist? The answer lies in what Mars lacks: plate tectonics. On Earth, the crust is constantly moving, shifting, recycling itself. Volcanoes like those in Hawaii are carried away from their magma source by tectonic drift, limiting their vertical growth. But on Mars, the crust is static, frozen. The magma plume beneath Olympus Mons remained fixed for billions of years, allowing lava to accumulate layer upon layer, building upward without interruption. Low gravity helped too, allowing the structure to reach heights that would collapse under their own weight on Earth. In stark contrast to this vertical monument lies the planet's deepest scar, Valles Marineris, the largest canyon system in the solar system. It stretches over 4,000 kilometers along the Martian equator, roughly 1/4 of the planet's entire circumference. In places, it spans 600 kilometers wide and plunges 8 kilometers deep. Earth's Grand Canyon, by comparison, is a mere scratch, only 800 kilometers long and less than 2 kilometers deep. Scientists now believe these two colossal features are connected. The Tharsis region, where Olympus Mons resides, underwent immense thickening as magma accumulated beneath the crust. This bulging created enormous stress on the surrounding terrain. Valles Marineris, they theorize, is a tectonic crack, a stress fracture that formed as the crust struggled to accommodate the weight and pressure of Tharsis, the greatest mountain and the largest chasm in the solar system, born from the same violent process. Twin scars on a planet whose heat cannot break its crust into mobile plates. They are eternal records of a unique, static planetary history, monuments to a world that followed a different evolutionary path, and they are waiting for humanity to arrive and stand in awe before them. The monuments of Mars stand eternal now, frozen in time, but they were not always silent. They were not always alone. Because billions of years ago, before the dust settled and the cold took hold, Mars was alive. Not with biology, perhaps, but with something equally profound: water. Liquid water. Vast quantities of it flowing across the surface, pooling in valleys, carving channels through ancient rock, and accumulating in the northern lowlands into what scientists now call Oceanus Borealis, the primordial ocean of Mars. The evidence is overwhelming. Orbiters have mapped extensive dry riverbeds snaking across the landscape. Rovers have photographed alluvial fans where ancient rivers deposited sediment. The Perseverance rover is currently exploring Jezero Crater, once home to a deep lake fed by a delta system so complex it rivals anything found on Earth. Scientists estimate that, in its youth, Mars held enough water to cover the entire planet in an ocean 100 to 1,500 meters deep, roughly half the volume of Earth's Atlantic Ocean, enough to sustain seas, lakes, rivers, and rainfall for millions of years. But the most compelling evidence comes from beneath the surface. The Chinese Zhurong rover, exploring the southern region of Utopia Planitia, detected something extraordinary with its subsurface radar dipping deposits. Angled layers of sediment pointing upward toward what would have been an ancient shoreline. These structures are unmistakable. They are identical to coastal sediments found on Earth, fossilized beaches. The thickness and arrangement of these layers suggests sustained wave action over potentially millions of years during the late Hesperian period. This is not abstract theory. This is concrete, recognizable geology. Somewhere beneath the rust-colored dust of Utopia, Planitia lies the ghost of an ancient sea, its waves long since stilled, its shores abandoned. Yet this ancient ocean presents a chemical puzzle. Orbital missions have searched extensively for carbonate minerals, the kind that should form when carbon dioxide dissolves in water and precipitates out over time. But the expected abundance is not there. The answer is unsettling. The early Martian oceans were likely acidic, highly acidic. In such conditions, carbonate minerals cannot form or persist. This changes everything. If life emerged in these ancient seas, it would have needed to be extremophilic, adapted to harsh chemistry, thriving in conditions that would destroy most terrestrial organisms. The ghost ocean of Mars was not a gentle cradle, it was a crucible. And then, catastrophically, it vanished. The water, the atmosphere, the warmth. All of it stripped away in a planetary collapse so total that Mars transformed from a wet, temperate world into the frozen desert we see today. The central culprit was the loss of the planet's magnetosphere. Around 4 billion years ago, Mars lost its global magnetic field, the protective shield generated by a dynamic molten core. Without this defense, the planet lay naked before the relentless assault of the solar wind. Charged particles from the sun slammed directly into the upper atmosphere, ionizing molecules and dragging them into space. This process, called atmospheric stripping, is not theoretical. Orbiting spacecraft have directly observed ionized atmospheric particles trailing away from Mars like a comet's tail, bleeding into the void. The atmosphere thinned, pressure dropped, temperatures plummeted. Today, Mars retains only a whisper of its former atmosphere. 96% carbon dioxide, thinner than the air found at 120,000 feet above Earth's surface, too thin to support liquid water, too thin to trap meaningful heat. The greenhouse effect collapsed, and Mars froze. But here's the revelation: atmospheric escape does not fully account for the disappearance of all that water. The dominant mechanism of loss was not outward to space, but inward to the crust. New research reveals that between 30 and 99% of Mars' initial water is still there, chemically locked within minerals deep in the regolith. As liquid water flowed across the surface over billions of years, it reacted with iron-rich rocks, forming hydrated minerals like clays, sulfates, and chlorides. The water was not lost. It was sequestered, trapped, stored in a planetary vault. This process precipitated a self-reinforcing collapse. As the atmosphere thinned and the planet cooled, the remaining liquid water accelerated chemical weathering reactions, which in turn drew atmospheric carbon dioxide out of the air. This carbon dioxide was progressively converted and locked into the clay-covered regolith as methane and other compounds. Estimates suggest that up to 1.7 bars of carbon dioxide, equivalent to about 80% of the planet's initial atmosphere, may now be chemically bound within the crust. The air did not escape. It was buried. This dual fate, water and air, are sequestered within the crust, while the solar wind stripped what remained, represents the central tragedy of Mars, a planet that should have been habitable, whose conditions paralleled early Earth, was robbed of its future, not by a single catastrophic event, but by the slow, grinding failure of its internal dynamo and the inexorable chemistry of its own surface. The thick atmosphere dissipated, the rivers dried, the ocean evaporated and froze and was chemically dismantled molecule by molecule until nothing remained but ice at the poles and hydrated minerals scattered across 1 billion square kilometers of regolith. Yet this tragedy carries within it a strange hope. Because the water is still there, and the carbon dioxide is still there. Future human missions could extract these trapped resources by heating the minerals, liberating the water and gases needed for survival. The sequestration process that killed Mars as a living world has inadvertently created a resource bank for the species that will one day attempt to resurrect it. The materials needed for human survival are not absent. They are merely sleeping, waiting beneath the rust-colored sands for the warmth of human ingenuity to awaken them once more. Mars appears dead. From orbit, it seems frozen in time, a static relic of ancient catastrophes. But appearances deceive, because despite its ancient crust and thin atmosphere, despite the loss of its ocean and the collapse of its climate, the Martian surface remains strangely, unexpectedly alive, not with biology, but with motion, with change, with processes unique to its cryogeological environment. The polar caps are the engines of this dynamism. They are not permanent fixtures, but breathing, expanding, contracting entities that respond dramatically to the seasons. During winter, temperatures plummet so severely that carbon dioxide in the already thin atmosphere freezes solid, falling as dry ice snow and accumulating in massive slabs across the polar regions. The caps expand, sometimes doubling in size. But when spring arrives and sunlight returns, the process reverses violently. The carbon dioxide does not melt, it sublimates. Solid ice transforms directly into gas, skipping the liquid phase entirely. This sublimation releases immense pressures and generates powerful winds that can reach the speeds of up to 400 kilometers per hour, continuously stirring and reshaping the dust and dunes across the entire planet. These sublimation winds are not gentle breezes. They are planetary-scale forces capable of lifting billions of tons of fine regolith into the atmosphere, sometimes creating dust storms so massive they obscure the entire globe from orbit, turning Mars into a featureless yellow sphere for months at a time. But the most bizarre manifestations of this sublimation engine are the so-called Martian spiders. Found primarily near the poles, these intricate web-like patterns are not biological, and they are not permanent. They are ephemeral scars left by escaping gas. The process begins in spring when sunlight warms the ground beneath a translucent layer of carbon dioxide ice. The solid carbon dioxide trapped underneath turns into high-pressure gas pressure builds. The ice above holds firm, until it does not. When the pressure finally exceeds the structural strength of the overlying ice, the gas erupts upward in a violent plume, scattering dark subsurface material across the bright ice in radiating spider-like patterns. These features range dramatically in size, from 45 meters to a full kilometer wide. They appear. They fade. They reappear with each seasonal cycle, ghostly signatures of a planet still breathing beneath its frozen surface. Beyond the poles, the atmosphere itself generates spectacle. Mars is prone to dust devils, miniature tornadoes that rapidly traverse the landscape, fueled by the rapid heating of the dark regolith under the thin atmosphere. While common dust devil plumes can reach 800 meters tall, the largest ever recorded was an astonishing 20 kilometers high in the Amazonas Planitia region. Even those observed more recently by rovers, such as the one Perseverance estimated to be 2 kilometers high based on its shadow length, significantly surpass the average terrestrial tornado in vertical scale. These vortices are not rare anomalies. They are common daily occurrences, visible in rover imagery as towering columns of dust spiraling upward against the pale sky. And the large-scale geological processes have not entirely ceased. High-resolution imagery confirms that massive avalanches continue to occur on steep dunes, some captured in the act of kicking up huge dust clouds, involving dunes 700 meters tall. The surface of Mars is not static, it is kinetic, shifting, responding to forces both atmospheric and geological, a world caught between its violent past and its frozen present, still animated by the energy of sublimation and the restless motion of wind and dust. Yet for all this dynamism, perhaps the most profound beauty of Mars reveals itself not during the day, but at twilight. The Martian sky offers a celestial aesthetic profoundly different from Earth's. providing moments of sublime beauty, counterintuitive to the terrestrial eye. While the daytime sky appears pale yellow-orange due to the pervasive rusty dust scattering red Lyle widely, the sunsets are defined by an inversion of color. As the sun dips below the horizon, the dust particles scatter blue light slightly more efficiently than other colors, causing the blue light to concentrate close to the sun's disk. The result is a striking, beautiful blue twilight, a phenomenon captured by rovers and symbolizing the planet's unique atmospheric optics. It is a reminder that even in a world as harsh and alien as Mars, there exists unexpected beauty. So Mars does not orbit alone. It is accompanied by two tiny, irregularly shaped moons, Phobos and Deimos, named after the Greek mythological twins, Fear and Dread, attendants of the war god Ares, Mars in Roman mythology. These satellites are thought to be captured asteroids. Substantially smaller than Earth's moon, Deimos is small and orbits far enough away to appear only as a distant star in the Martian sky. But Phobos is sealed to a far more dramatic and finite destiny. It orbits Mars at an extraordinarily close distance, only 6,000 kilometers above the surface, closer to its planet than any other moon in the solar system. This extreme proximity places it deep within the grasp of Mars's tidal gravity. The planet's gravitational pull drawing Phobos inward at a rate of roughly 2 meters every century. Scientists have determined that the long, shallow grooves scarring the surface of Phobos are not impact fractures as once believed, but stretch marks resulting from these relentless tidal forces, indicating that the structural failure of the moon has already commenced. The cosmic clock is ticking for Phobos. Within 30 to 50 million years, the tidal forces will become too great, tearing the small rubble pile moon apart. This inevitable destruction will result in a temporary, magnificent planetary ring system around Mars, which is predicted to persist for anywhere from 1 million to 100 million years. Thus Mars, the planet that experienced the cosmic tragedy of losing its life-sustaining ocean billions of years ago, is set to gain a splendid Saturn-like accessory in the cosmic near future, profoundly altering the vista for its future inhabitants. A world of loss will become a world of spectacle. Fear and dread will become dust and light, encircling the red planet in a glittering halo visible from the surface below. The question burns at the heart of every mission to Mars. Every orbiter, every lander, every rover that has traced tire tracks across ancient lake beds, the question that justifies the expense, the risk, the decades of patient engineering. Were we ever alone? Did life in any form ever arise on the surface of Mars when the oceans were still full and the atmosphere still thick? Or has Earth always been the sole cradle of biology in our corner of the cosmos? The search for this answer is not abstract philosophy, it is concrete chemistry. Because life, at its foundation, is not mystical, it is molecular. Complex organic molecules arranged in specific patterns, capable of self-replication and metabolic function. And so the question becomes simpler, more tractable. Did the complex chemical reactions required for life advance on Mars when liquid water was abundant? Did prebiotic chemistry progress far enough to cross the threshold into true biology? The evidence gathering began decades ago, but it accelerated dramatically with the arrival of the Curiosity rover in Gale Crater. In 2012, Gale Crater is not just any impact basin. It is an ancient lake bed, a place where water once pooled for millions of years, fed by rivers carrying sediment from the surrounding highlands. If life emerged anywhere on Mars, this would be a prime candidate. Curiosity's mission was clear: drill into the sedimentary rock, analyze the chemistry, search for organic molecules, and it found them. not simple organics, not the basic 2-carbon or 3-carbon molecules that can form through purely geological processes, but long-chain hydrocarbons, decane, undecane, dodecane, molecules containing 10, 11, and 12 carbons respectively. These are the largest organic molecules yet discovered on the Red Planet, and their significance cannot be overstated. Scientists believe these molecules are fragments of fatty acids, the critical chemical building blocks that terrestrial life uses to form cell membranes and perform various cellular functions. The discovery of these larger, more complex compounds suggests that prebiotic chemistry on Mars advanced significantly toward the complexity required for an origin of life during its warmer, wetter Hesperian period. But here is the frustration, the ambiguity, the maddening incompleteness of the evidence. Because it is currently impossible to confirm whether these molecules were formed by living organisms, what scientists call biogenic origins, or through non-living geological processes, what they call abiotic synthesis. Both pathways can produce the same molecules. Hydrothermal vents, where hot water reacts with minerals deep underground, can synthesize complex organic compounds without any involvement of life. Ultraviolet radiation interacting with simple carbon dioxide and water can create organic precursors. The chemistry alone cannot definitively distinguish between life and non-life. This ambiguity is the impetus for the most ambitious phase of Martian exploration. Sample return. The Perseverance rover, which landed in Jezero crater in February 2021, is not merely analyzing rocks, it's collecting them. Coring samples from carefully selected locations and sealing them in sterile tubes. Jezero crater was chosen because it once held a vast lake fed by an ancient river system that deposited thick sediments in a delta environment. This delta, visible from orbit as a fan-shaped deposit of layered rock, is considered a prime location for trapping and preserving ancient microbial biosignatures. If microbes lived in the waters of Jezero 3.5 billion years ago, their chemical traces may still exist within these rocks, but to determine definitively whether those traces are biological or geological requires instruments that do not yet exist on Mars. It requires the full analytical power of Earth-based laboratories. Instruments capable of measuring carbon isotope ratios with extreme precision microscopes, capable of resolving microstructures at the nanometer scale. Chemical analyzers capable of detecting biomarkers that are a diagnostic of a life. The samples Perseverance is collecting must be retrieved and brought back to Earth. This is the plan. A future mission, still in development, will land near Perseverance's cache, collect the sample tubes, launch them into Martian orbit, rendezvous with an orbiting spacecraft, and return them to Earth for analysis. It is staggeringly complex. It is extraordinarily expensive, but it is necessary. Because the true determination of whether Martian life once existed hinges on this retrieval. The stakes are cosmic. If those samples contain definitive biosignatures, if the isotope ratios are inconsistent with abiotic processes, if the microstructures resemble fossilized cells, then the conclusion is unavoidable. Life arose independently on Mars. And if life arose independently twice in a single solar system, then the universe is almost certainly teeming with biology. The Fermi paradox intensifies. The Drake equation shifts. Humanity's place in the cosmos fundamentally changes. But if the samples are sterile, if the organic molecules are purely abiotic, if no trace of biological activity can be found even in the most promising locations, then we face a different revelation. That life is rarer than we hoped. That the leap from chemistry to biology requires conditions so specific, so delicate, that even Mars, with its oceans and rivers and temperate climate, could not make the crossing. That Earth may be unique not because it is the only world with water and organic chemistry, but because it is the only world where that chemistry succeeded in becoming life. Either answer transforms our understanding. Either answer justifies the decades of exploration, the missions lost, the billions spent. Because the question of whether we are alone is not merely curiosity, it is existential. And Mars, more than any other world in our reach, holds the answer locked within its ancient sediments, waiting for humanity to finally ask the right questions in the right way with the right tools. The echoes of chemistry, whether biological or geological, are waiting to be heard. The ultimate human aspiration for Mars extends beyond exploration, beyond scientific discovery, beyond even the establishment of research outposts. The ultimate dream is transformation, to engineer the planet itself, to raise the temperature, to thicken the atmosphere, to stabilize the liquid water on the surface, to create, in essence, a second Earth. This concept, terraforming, has captivated scientists and visionaries for decades, a world remade by human ingenuity, a planetary resurrection. But the discoveries regarding Mars's volatile loss have introduced massive practical limitations and profound ethical questions that challenge this dream at its foundation. The engineering challenge begins with resources. Early theories of terraforming suggested that mobilizing the carbon dioxide trapped in the polar ice caps could kickstart a runaway greenhouse effect. The logic was elegant. Release enough carbon dioxide into the atmosphere to increase pressure and trap heat. As temperatures rise, more carbon dioxide sublimates from the caps, accelerating the warming in a positive feedback loop. Eventually, liquid water becomes stable. Plants could theoretically be introduced. The atmosphere would continue to thicken. Mars would bloom. But contemporary analysis reveals a fatal flaw. The accessible reserves of carbon dioxide in the polar caps in the upper regolith are insufficient, nowhere near enough to provide a significant warming. Most of the necessary carbon dioxide and water are not sitting on the surface waiting to be released. They are chemically locked within minerals and clays deep in the crust, sequestered through billions of years of weathering reactions. To liberate these sequestered volatiles would require heating immense tracts of the Martian crust to temperatures sufficient to break molecular bonds and release the trapped gases and water. The energy requirement is staggering, far beyond anything current technology can deliver on a planetary scale. Some have proposed alternative strategies, importing and deploying potent non-carbon dioxide greenhouse gases, such as chlorofluorocarbons, could theoretically warm the planet without requiring massive volumes, but these gases have relatively short atmospheric lifetimes due to photodissociation by ultraviolet radiation. They would require constant replenishment, an industrial effort that would need to persist for thousands of years. The logistical and economic burden renders this approach impractical with present-day capabilities. The focus, therefore, shifts from planetary-scale terraforming to localized in situ resource utilization. Instead of attempting to remake an entire world, future settlements will extract sequestered water and carbon dioxide from local regolith, heating minerals to release the volatiles needed for closed-loop life support systems. This is achievable. This is practical. But it is not terraforming. It is survival. Yet beyond the engineering impossibility lies an even more complex frontier ethics. The debate over terraforming pits pragmatic human interest against conservationist philosophy, and the arguments on both sides carry profound weight. Proponents argue that humanity has a moral obligation to expand life beyond Earth. Life is fragile. Earth has experienced multiple mass extinctions. A sufficiently large asteroid impact, a nearby supernova, or the eventual evolution of the sun into a red giant will render Earth uninhabitable. Spreading terrestrial life to other worlds is not hubris. It is a survival imperative. Mars, they argue, is effectively dead. Its surface is sterile, its atmosphere is gone. No indigenous biosphere exists. Therefore, there is no ethical violation in repurposing the planet for human use. Transforming Mars would be a continuation of life's natural history of reshaping environments, from cyanobacteria oxygenating Earth's atmosphere billions of years ago to humans cultivating agriculture and building cities. Conversely, critics raise serious concerns about the anthropocentrism and irreversibility of such actions. The risk is profound. What if indigenous Martian life does exist, dormant or hidden in subsurface aquifers or deep within the regolith? If the astrobiological research currently underway were to confirm the existence of ancient or even extant microbial life, the decision to terraform shifts fundamentally. It becomes a decision to actively disrupt, and potentially render extinct, a separate biosphere. Even if that life is only microbial, its scientific value is incalculable. A second genesis, independent biology, proof that life arises wherever conditions permit. To destroy such a discovery for human convenience would be an act of cosmic vandalism. Moreover, even if Mars is confirmed to be sterile, some argue that humanity has no inherent right to remake alien worlds in our image, that Mars has value as it is, that we should approach other planets with humility, not dominance, that the urge to terraform reflects a dangerous impulse to conquer rather than coexist. The ethical debate cannot be resolved with data alone. It is fundamentally a question of values. Do we prioritize human survival and expansion above all else? Or do we prioritize the preservation of alien environments, even dead ones, as cosmic heritage sites? The answer may depend on what the sample return missions reveal. If Martian life is confirmed, the ethical calculus tilts decisively toward preservation. If Mars is sterile, the argument for transformation strengthens, but even in the case of confirmed sterility, practical constraints remain overwhelming. Terraforming Mars with current or near future technology is not feasible. The resources are sequestered. The energy requirements are prohibitive. The timescales stretch across millennia. Humanity may eventually develop the technological capability to remake worlds, but that day is not imminent. The path forward demands humility, rigorous science, and a deep appreciation for the unique history preserved beneath the rust-colored sands. Future exploration must move beyond simply characterizing Mars to understanding its precise astrobiological past. Only when we know definitively whether life ever existed can we make informed decisions about intervention. The greatest challenge for humanity is reconciling the dream of a second home with the limitations of planetary physics and the weight of cosmic ethics. Mars is not a blank canvas. It is a world with a history. And that history, whether it includes life or not, deserves to be understood before it is altered. Mars is a world defined by its titanic scale and its profound history of loss. It stands as a monument to what could have been, a planet that began much like Earth, with thick skies and flowing water and chemistry complex enough to perhaps spark life. But where Earth flourished, Mars faltered. Its dynamo failed. Its magnetic shield collapsed. The solar wind stripped its atmosphere. The water, that essential ingredient for life, did not vanish into space, as once believed, but instead sank inward, chemically locked within minerals scattered across 1 billion square kilometers of regolith. The story of Mars is written in rust and stone, and ancient riverbeds and fossilized shorelines, and mountains that dwarf Everest and canyons that make the Grand Canyon look like a scratch on the surface. It is a story that has taken humanity centuries to begin deciphering, from the first telescopic observations of Christian Huygens in the 17th century to the robotic emissaries that now roam its surface, drilling into lake beds and analyzing the chemistry of rocks that have not moved in billions of years. The synthesis of recent data confirms that Mars operates under a unique set of physical laws. Its static crust, frozen for billions of years, without the recycling motion of plate tectonics, yielded mountains and canyons of impossible scale. Olympus Mons towers 22 kilometers above the surrounding plains, 3 times higher than Everest, stretching 600 kilometers across, so wide that if you stood at its summit, you could not see its base. The curvature of Mars itself would hide the volcano's true shape from your eyes. Its flanks slope at only 5 degrees, creating an illusion of flatness until you reach the edge, where the ground drops away in a sheer cliff plunging 8 kilometers straight down. In a dramatic opposition lies Valles Marineris, stretching over 4,000 kilometers along the Martian equator, roughly 1/4 of the planet's entire circumference. In places it spans 600 kilometers wide and plunges 8 kilometers deep. These are not merely geological features. They are cosmic monuments to a world that followed a different evolutionary path, where magma plumes remained fixed and stress fractures grew into planetary scars. Scientists now believe these 2 colossal features are connected, born from the same violent process. The Tharsis region, where Olympus Mons resides, underwent immense thickening as magma accumulated beneath the crust. This bulging created enormous stress on the surrounding terrain. Valles Marineris is theorized to be a tectonic crack, a stress fracture that formed as the crust struggled to accommodate the weight and pressure of Tharsis, the greatest mountain and the largest chasm in the solar system, eternal records of a unique, static, planetary history. Yet beneath the stillness, Mars remains strangely active, driven not by volcanic heat or tectonic movement, but by the volatile dynamics of solid carbon dioxide. The polar caps, composed of water ice and seasonal carbon dioxide frost, expand and contract dramatically with the seasons. During winter, temperatures plummet so severely that carbon dioxide in the already thin atmosphere freezes solid, falling as dry ice snow and accumulating in massive slab across the polar regions. The caps expand, sometimes doubling in size. But when spring arrives and sunlight returns, the process reverses violently. The carbon dioxide does not melt, it sublimates. Solid ice transforms directly into gas, skipping the liquid phase entirely. This sublimation releases immense pressures and generates powerful winds that can reach speeds of up to 400 kilometers per hour, continuously stirring and reshaping the dust and dunes across the entire planet. These sublimation winds are not gentle breezes. They are planetary-scale forces capable of lifting billions of tons of fine regolith into the atmosphere, sometimes creating dust storms so massive they obscure the entire globe from orbit, turning Mars into a featureless yellow sphere for months at a time. The surface is kinetic, animated by forces unique to its cryogeological environment. The most bizarre manifestations of this sublimation engine are the so-called Martian spiders, found primarily near the poles. These intricate web-like patterns are not biological, and they are not permanent. They are ephemeral scars left by escaping gas. The process begins in spring when sunlight warms the ground beneath a translucent layer of carbon dioxide ice. The solid carbon dioxide trapped underneath turns into high-pressure gas. Pressure builds. The ice above holds firm until it does not. when the pressure finally exceeds the structural strength of the overlying ice. The gas erupts upward in a violent plume, scattering dark subsurface material across the bright ice in radiating spider-like patterns. These features range dramatically in size. From 45 meters to a full kilometer wide, they appear. They fade. They reappear with each seasonal cycle, ghostly signatures of a planet still breathing beneath its frozen surface. Beyond the poles, the atmosphere itself generates spectacle. Dust devils, miniature tornadoes rapidly traverse the landscape, fueled by the rapid heating of the dark regolith under the thin atmosphere. While common dust devil plumes can reach 800 meters tall, the largest ever recorded was an astonishing 20 kilometers high in the Amazonas Planitia region. These vortices are not rare anomalies. They are common daily occurrences, visible in rover imagery as towering columns of dust spiraling upward against the pale sky. And above it all hangs the specter of Phobos, the doomed moon. Named after the Greek god of fear, this irregularly shaped satellite orbits Mars at an extraordinarily close distance, only 6,000 kilometers above the surface, closer to its planet than any other moon in the solar system. This extreme proximity places it deep within the grasp of Mars's tidal gravity. The planet's gravitational pull is drawing Phobos inward at a rate of roughly 2 meters every century. Scientists have determined that the long, shallow grooves scarring the surface of Phobos are not impact fractures, as once believed, but stretch marks resulting from these relentless tidal forces, indicating that the structural failure of the moon has already commenced. The cosmic clock is ticking for Phobos. Within 30 to 50 million years, the tidal forces will become too great, tearing the small rubble pile moon apart. This inevitable destruction will result in a temporary magnificent planetary ring system around Mars, which is predicted to persist for anywhere from 1 million to 100 million years. Thus Mars, the planet that experienced the cosmic tragedy of losing its life-sustaining ocean billions of years ago, is set to gain a splendid Saturn-like accessory in the cosmic near future. A planet of loss will become a planet of spectacle. Fear and dread will become dust and light, encircling the red planet in a glittering halo visible from the surface below. The search for life has progressed from locating simple organics to finding complex, long-chain building blocks in ancient lake beds. Curiosity's discovery of decane, undecane, and dodecane, molecules containing 10, 11, and 12 carbon atoms, respectively 11, and 12 carbons respectively. Potential fragments of fatty acids suggest that prebiotic chemistry on Mars advanced significantly toward the complexity required for an origin of life during the Hesperian period. These are the largest organic molecules yet discovered on the red planet. Their significance cannot be overstated, because fatty acids are the critical chemical building blocks that terrestrial life uses to form cell membranes and perform various cellular functions. The greatest challenge for humanity is reconciling the dream of a second home with the limitations of planetary physics and the weight of cosmic ethics. The dream of terraforming, of transforming Mars into a habitable world, has captivated imaginations for decades. But the discoveries regarding volatile sequestration have introduced massive practical barriers. The carbon dioxide and water needed to thicken the atmosphere and warm the planet are not readily accessible. They are chemically bound within the crust, requiring energy inputs far beyond current technological capabilities to liberate on a planetary scale. Contemporary plans focus not on planetary transformation, but on localized survival. In situ, resource utilization. Extracting water and carbon dioxide from regolith to support closed-loop settlement, building radiation-shielded habitats to protect against the cosmic rays that ceaselessly bombard the unprotected surface. synthesizing methane fuel from atmospheric carbon dioxide and subsurface water ice to enable return journeys. These are achievable goals. These are the foundations upon which the first Martian settlements will be built. NASA's reimagined future for Mars exploration emphasizes smaller missions, more commercial and international engagement, and defining science goals for an era of human presence on Mars. The traditional model of large flagship missions is giving way to a sustainable program with missions launching at every 26-month opportunity when Mars and Earth are correctly aligned. But beyond the engineering challenges lie the ethical questions that cannot be resolved with data alone. If indigenous Martian life is discovered, even in dormant or microbial form, does humanity have the right to introduce terrestrial organisms and technologies that could render it extinct? The risk is profound. A second Genesis, independent biology, proof that life arises wherever conditions permit. To destroy such a discovery for human convenience would be an act of cosmic vandalism. Yet proponents of expansion argue that humanity has a moral obligation to spread life beyond Earth. Life is fragile. Earth has experienced multiple mass extinctions. A sufficiently large asteroid impact, a near-eye supernova, or the eventual evolution of the Sun into a red giant will render Earth uninhabitable. Spreading terrestrial life to other worlds is not hubris. It is a survival imperative. The decisions we make will establish precedents that echo across centuries. The path forward demands rigorous science, technological innovation, and philosophical maturity. Future exploration must move beyond characterizing Mars to understanding its precise astrobiological past. Only when we know the truth can we make informed decisions about intervention. Mars is not a blank canvas. It is a world with a history written in rust-colored dust and ancient riverbeds, a history of rising and falling temperatures, of oceans that filled and emptied, of chemistry that advanced to the very threshold of biology and perhaps beyond, and humanity stands at the threshold, preparing for the most ambitious journey in our history. Not merely to visit Mars, but to understand it, to learn from its failures and its successes, to determine whether it once cradled life. The Crimson Dream is not merely about survival or expansion. It is about our maturity as a species, about whether we can reach another world, and do so with humility, respect, and appreciation for the cosmic significance of what we find. The monuments stand waiting, the sequestered water lies dormant. The fossilized shorelines preserve their secrets beneath the regolith. And we, fragile and hopeful, prepare to answer the oldest question humanity has ever asked: are we alone?